Imagine, for just a second, that you are standing on the deck of a massive cargo ship. Or, maybe you're leaning over the railing of one of those really nimble passenger ferries.
Right, just looking out.
Yeah, exactly. You're looking down at the dark water and you can feel that deep rhythmic hum of the main engine, like it's vibrating all the way up through the steel deck right into your boots.
Oh, yeah, you can always feel it in your boot.
It's unmistakable.
Hmm.
But have you ever actually stopped to wonder how thousands of tons of heavy metal gracefully navigate across these violent, unpredictable oceans, and then, after all that, somehow manage to tightly parallel park into a concrete harbor without just completely crushing the dock?
It is honestly a modern marvel, and it
Mhm.
completely hides in plain sight. We tend to look at a ship and we just see a floating building, basically.
Right, a giant steel box.
Exactly. But what we miss is the invisible, incredibly violent world of fluid dynamics and the sheer mechanical genius operating just beneath the waterline that actually makes all that movement possible.
And uncovering that hidden underwater world is our mission for today. We are doing a deep dive into a highly technical engineering document. Specifically, we're looking at Chapter 12, Rudders, Propellers, and Thrusters.
That's the one.
We are going to demystify the surprisingly elegant physics that keep global shipping afloat, moving, and steering. So, okay, let's unpack this.
Well, the hardware we are going to explore, it might seem really straightforward at first glance. Just huge pieces of metal spinning or turning in the water.
Yeah, big fan, big fin.
Yeah.
Seems simple enough?
Right, but the engineering trade-offs required to actually conquer the ocean are endlessly complex.
I bet. So before a ship can, speed across the open water, it needs to actually know how to point itself in the right direction. I mean, it absolutely doesn't matter how much horsepower you have if you are just driving in huge circles.
Very true.
So we're going to start at the very back of the ship, the stern, the aft. We are talking about the rudder.
Yeah, the rudder is fixed on the aft of the hull, usually located right behind the propeller. Now, a really common misconception here is that a rudder works by physically pushing the back of the ship around.
Almost like a giant canoe paddle.
Exactly like a canoe paddle. People think it just shoves the water out of the way.
Yeah.
But the actual physics are entirely different.
Wait, really? It's not pushing the water.
Mechanically, no. It is all about fluid dynamics. When you angle the rudder across the flow of the rushing water coming off that propeller, you create a pressure difference.
Oh, a pressure difference.
Right. The water accelerates over one side of the curved blade, which creates lower pressure, while the water on the opposing side, it slows down, creating higher pressure.
Got it.
And that invisible differential in pressure is what actually pulls and forces the ship to turn in the desired direction.
Oh, wow, that makes so much sense. I mean, think about it like this for anyone listening. You're riding in a car on the highway, right? And you stick your hand out the window.
Oh, that's a great example.
Right, because if you hold your hand perfectly flat, slicing through the air, it just cuts right through. But the second you angle your hand, just a tiny bit, tilting your palm up or down.
The wind pressure instantly catches it.
Exactly. It forces your entire arm sharply up toward the roof or down toward the road. You aren't pushing the wind, you are changing the pressure, and the pressure forcefully moves your arm.
That is a brilliant way to visualize it.
Right.
I mean, take that exact same aerodynamic principle, but replace the thin air of the highway with dense, heavy seawater.
Oh, man. It's a lot heavier.
Way heavier.
Yeah.
And then replace your hand with a slab of solid steel that can be, several stories tall. The forces generated by that underwater pressure difference are astronomical.
I can't even imagine. But if the water pressure is doing all that heavy lifting, that implies the physical machinery inside the ship. The stuff turning that massive steel hand must be under immense strain.
Oh, absolutely. And it turns out engineers have come up with different ways to ease that strain. It's based entirely on where the rudder's surface area sits relative to its turning axis.
Okay, turning axis. Break that down for us.
Sure. The turning axis is simply the vertical line that the rudder pivots around, basically the hinge.
Okay.
If you put the entire surface area of the rudder behind that pivot point, like a door swinging on a wall hinge, you have what is called an unbalanced rudder.
Unbalanced, meaning it's all trailing behind the hinge.
Right. And because of that, the steering engine inside the ship has to do all the heavy lifting to fight the rushing current and literally hold that door open against the water.
Which sounds incredibly inefficient for a massive vessel.
It is. It requires massive mechanical force. So engineers started shifting the pivot point backward.
Oh, interesting.
Yeah, if you move the turning axis so that a significant portion of the blade's area, specifically 25 to 30% of it, is actually sticking out forward of the pivot point, you create a balanced rudder.
Wait, so the rushing water actually hits that forward-facing part of the blade and helps push it into the turn?
You got it. The ocean is basically helping the steering motor do its job.
That is so smart.
What's fascinating here is how moving a pivot point by just a few feet fundamentally transforms the mechanical requirements of the entire steering system. The water pressure balances out the shear torque.
Is there a middle ground between those two?
There is actually. It's called the semi-balanced rudder. It still has some surface area forward of the turning axis, but it's a much smaller proportion, like less than 20% of the total lateral area.
Okay, so speaking of those mechanical requirements, let's actually follow that force, because you have the steering machinery deep inside the hull of the ship.
Right, usually in the steering gear room.
Yeah. But how does it physically connect to this giant slab of steel hanging out in the ocean? Because the anatomy of this setup from the source text paints quite a picture.
It requires a chain of really highly specialized components. It starts with the stock.
The stock, okay.
Yeah, this is essentially a massive vertical steel column that acts as the main drive shaft.
Mm.
It transfers the rotational force from the steering gear inside the ship straight down to the rudder blade outside the ship.
And to get outside, that stock has to pass through the bottom of the hull, right? Through a watertight rudder trunk.
Exactly. And then you have the bearings, the upper and lower bearings. They are specifically designed to handle the sheer, crushing vertical weight of the entire rudder assembly.
Because it's a huge piece of metal just hanging there.
Right. And you also need components purely for maintenance. There is a lifting tube fitted into the structure, which allows heavy shipyard cranes to safely grab and lift the massive rudder during installation or, dry dock repairs.
Makes sense. You can't exactly lift that by hand.
No, definitely not. You'll also find drain plugs to empty out any trapped water when the ship is out of the ocean. And finally, anchoring the whole thing at the pivot point, you have the pintle. That's a colossal pin or bolt acting as the primary hinge.
Okay, I need to pause you right here. Because just visualizing this layout is setting off like major warning bells in my head.
Uh-oh. Why is that?
Well, we are talking about an immensely heavy piece of steel hanging off the back of a moving ship in a highly corrosive, incredibly violent saltwater environment.
Yes.
And the entire vertical weight rests on these bearings, pivoting on a single pintle pin, and the stock passes directly through a trunk right into the inside of the hull. I mean, isn't that an absolute nightmare of a structural weak point?
I see where you're going with this.
It sounds like putting a giant hole in the bottom of a boat and just hoping it doesn't shear off.
You have actually zeroed in on one of the greatest enduring anxieties of naval architecture.
Really? So I'm not crazy.
No, not at all. Hanging a multi-ton slab of metal outside a hole in your hull on a hinge is structurally audacious. It is a known vulnerability.
I'd call it terrifying.
But this is where the sheer robustness of marine engineering comes into play. That watertight trunk is heavily reinforced, and it's packed with heavy-duty seals that are constantly monitored for pressure drops.
Okay, so they're keeping a very close eye on it.
Oh, constantly. And the pintle and bearings are not just off-the-shelf hardware. They are forged from specialized alloys designed specifically to handle constant multi-directional stress.
So it's heavily over-engineered.
Incredibly over-engineered.
Yeah.
Because the alternative, having absolutely no directional control in the open ocean, is a guaranteed disaster.
Fair enough. I'll take the heavily monitored hole in the boat over drifting helplessly. So we have the rudder sorted. We know how the ship points itself.
Right.
But pointing is completely useless if you aren't moving. We need to explore what actually generates the thrust to move a metal mountain forward. So we move from the rudder to the driving force.
The propeller.
Yes, the propeller. At its core, a marine propeller is a rotating fan-like structure used to propel the ship by utilizing the power generated and transmitted by the main engine.
But, you can't just use standard iron or cheap steel to build these giant underwater fans, right?
Yeah.
They're operating in a uniquely hostile environment.
Very hostile. The source material mentions engineers use very specific materials. Things like alloys of aluminum and stainless steel, or specialized combinations of nickel, aluminum, and bronze.
There is a brilliant metallurgical reason for those specific choices. A propeller is constantly fighting two distinct enemies at all times.
Okay, what are they?
First, severe chemical corrosion from the salt water, just constantly eating away at it. And second, the sheer physical stress of torque. You have a massive engine twisting this metal against the resistance of millions of gallons of water.
Right, because water is heavy.
Exactly. So those specific alloys provide essentially the golden ratio for marine propulsion. They are exceptionally lighter than other heavy metals.
So the engine doesn't waste energy just trying to spin the dead weight of the blades.
You got it.
Yeah.
Yet they possess a much higher yield strength to avoid bending or snapping under that aquatic torque.
That makes total sense. Now hold on, because I'm trying to visualize the next structural category we have here, which is pitch.
Ah, yes. Pitch is crucial.
The pitch is essentially the angle of the propeller blades, right? And the most common type is the fixed pitch propeller, or the FPP. That makes total sense to me. It is cast as one solid, unchangeable shape.
Correct. It's widely used because of its simple structure, lightweight, cost-effectiveness, and, easy maintenance. It's just a single chunk of metal doing its job.
Right. But then we get to the controllable pitch propeller, the CPP.
On a CPP, the pitch angle of the individual blades can actually be varied and rotated on the hub, either hydraulically or electrically.
Wait. How can a solid metal blade change its angle while it's actively spinning under thousands of tons of water pressure? That sounds impossible.
It is a marvel of internal mechanics, honestly. The central hub of a controllable pitch propeller isn't just a solid lump of steel. It contains a complex sealed hydraulic system that connects to the base of each individual blade.
Oh, wow. Inside the hub itself.
Inside the hub. By pumping hydraulic fluid, the ship's bridge can independently twist the blades on their axis. They can cut through the water at a steeper or shallower angle, all while the entire propeller continues to spin at full speed.
Here's where it gets really interesting. Think of the difference between these two propellers like riding a bicycle.
Okay, I like this.
The fixed pitch propeller is basically a single-speed beach cruiser. You pedal, it goes. To go faster, you have to pedal your legs faster. To go slower, you pedal slower. The speed of the engine directly dictates the speed of the ship.
Exactly. And that's fine for cruising at a steady pace, but engines have specific RPM bands where they burn fuel most efficiently.
Right, so a main engine forced to constantly throttle up and down is just wasting a massive amount of fuel.
A huge amount.
So the controllable pitch propeller is like a multi-gear mountain bike. By adjusting the pitch angle of the blades in the water, the ship can use power incredibly efficiently. You use a high aggressive pitch for high vessel speed, taking bigger bites of the water. You use a low pitch for low vessel speed. And you can do all of this without having to constantly throttle the massive main engine up and down.
The engine can just hum along at its optimal, most fuel-efficient RPM. And the propeller blades do the work of shifting gears by changing their angle. It allows for incredible control and fuel efficiency.
It's brilliant.
But of course, there's a trade-off. A controllable pitch hub with all those internal hydraulics is vastly more complicated, expensive, and difficult to maintain than a solid, fixed pitch casting.
Right. Moving parts mean more things that can break.
Always.
Well, since we are talking about efficiency, how do engineers squeeze every single drop of forward momentum out of that engine? Because the text notes, a lot of it comes down to the shape, the count, and the configuration of the blades.
It does. Propellers can have 2, 3, 4, or even more blades.
And there is a golden rule in marine architecture here, right? Generally, the more blades a propeller has, the better its power efficiency.
Yes. By adding more blades, you distribute the immense thrust over a larger total surface area. It reduces the physical load on each individual blade.
Which I assume makes it run smoother.
Exactly. It lessens vibration and dramatically smooths out the power delivery into the water.
But it's not just about slapping more blades on a hub, though. How the propeller is actually installed onto the ship dramatically alters how it interacts with the fluid dynamics of the ocean.
Oh, the installation method changes everything.
Right, so the first method is the standard on-shaft setup. The propeller is simply installed directly onto the tail shaft protruding from the hull.
That is the standard configuration you see on almost any boat. But fluid dynamics engineers realized that a bare, exposed propeller wastes a lot of energy.
Which brings us to the second method, the ducted propeller, also known as a quart nozzle.
Quart nozzle, yes.
This is where the propeller is installed inside a round hydrodynamic ring or nozzle that completely encircles the spinning blades. But why does putting a ring around it make it so much more power efficient?
It solves the problem of tip vortices.
Tip vortices.
Yeah. Water naturally wants to move from an area of high pressure to low pressure. So as a bare propeller spins, water tends to slip off the very outer tips of the blades, spiraling outward into the ocean.
So it's just pushing water out sideways instead of backward?
Exactly. It's wasted kinetic energy.
Yeah.
But the duct forms a physical hydrodynamic barrier. It traps that escaping water and forces it directly straight backward, creating a much more concentrated, powerful column of forward thrust.
That's amazing. I love how these designs just keep capturing wasted energy because the third installation method, contra-rotating propellers, takes that concept to the absolute extreme.
Oh, the contra-rotating setup is brilliant.
This is where you install two completely separate propellers facing each other, operating on the exact same propeller shaft line, but they spin in completely opposite directions.
Right. And if we connect this to the bigger picture of fluid dynamics, we see exactly why this is done. When a single propeller spins, it doesn't just push water straight back.
It doesn't.
No, it creates a massive rotational vortex, a violently swirling wake of water spinning in the same direction as the blades.
Oh, so the engine is burning expensive fuel just to spin water in a circle instead of pushing the ship straight ahead.
Exactly. But with a contra-rotating setup, the second propeller spinning in the opposite direction essentially catches that swirling vortex from the first propeller.
Oh, wow.
It straightens out the water flow, recovering that lost rotational energy.
Mm-hmm.
By rotating in opposite directions, they save flow loss, making the propulsor highly effective.
Okay, basic logic forces me to ask a question right here.
Let's hear it.
If the golden rule is that more blades equal better power efficiency, and putting a propeller in a duct makes it more efficient, and contra-rotating propellers are incredible at saving flow loss, why don't massive global cargo ships just use giant multi-blade ducted contra-rotating setups?
That's a fair point.
I mean, fuel is the biggest cost in shipping. Shouldn't they use the absolute most theoretically efficient machine possible?
It is a totally logical deduction based purely on the physics. But it ignores the brutal reality of heavy engineering. Because the contra-rotating propeller is so complicated in structure, it is actually not widely used on large vessels.
Ah, complexity is the enemy of scale.
Imagine trying to engineer a shaft within a shaft capable of delivering tens of thousands of horsepower, spinning massive opposing blades in a corrosive saltwater environment while hanging off the back of a ship the size of a skyscraper.
Yeah, okay, that sounds like a maintenance nightmare.
It becomes a total nightmare. The potential for catastrophic mechanical failure, the sheer weight of the intricate gears required inside the hull, it's just too much. Sometimes ultimate simplicity, like the single massive fixed-pitch propeller, beats pure mechanical perfection when you scale it up to Leviathan proportions.
Reliability always wins.
Always.
You definitely don't want a hyper-complex dual propeller system snapping a gear in the middle of a Pacific storm.
Definitely not.
So we've conquered open ocean transit, we have our massive rudder pointing us, and our simple, reliable propeller pushing us efficiently across thousands of miles. But what happens when that exact same metal mountain reaches its destination?
The port.
Right. What happens when it enters a tiny, shallow, incredibly crowded port? Parallel parking a freight train is not easy.
No, it isn't. And that traditional propulsion system suddenly becomes a massive liability.
Really? A liability?
Yes, because a gigantic propeller pushing millions of gallons of water over a huge rudder is a blunt instrument. It is designed for maximum forward momentum at sea. It is completely useless for a delicate, inch-by-inch maneuvering against a concrete dock.
You need micro-maneuvering. And that brings us to the final piece of the puzzle from the text. Maneuvering thrusters.
Also commonly known as bow and stern thrusters. These represent a completely different philosophy of propulsion. They are transversal propulsion devices.
Transversal meaning they direct thrust side to side rather than forward and back.
Exactly. They are literally tunnels built directly right through the hull of the ship, from port to starboard, with a smaller propeller tucked inside that tunnel.
So it's just pushing water sideways through the boat.
Right. They are specifically designed for better maneuverability of the vessel at much lower speeds.
Yep.
If you use a bow thruster to push the front of the ship to the right and a stern thruster to push the back of the ship to the left.
A massive vessel can essentially crab walk sideways perfectly into a berth.
Exactly.
You know, if you are listening to this and you've ever been on a cruise ship or watched one dock, you might have noticed a sudden, violent bubbling of water erupting out from the side of the hull right before it touches the pier.
Oh yeah, it stirs up the water quite a bit.
That is the transversal thruster blasting water out of the tunnel to gently push thousands of tons of steel sideways. But engineers didn't stop there, right? There is an ultimate maneuvering tool that takes agility to the absolute maximum. The azimuth thruster.
The azimuth thruster is fascinating because it completely eliminates the need for a traditional rudder altogether.
Wow. It's defined as a propeller that can be rotated horizontally through a full 360 degrees. This allows the thrust to be generated in absolutely any desired direction.
Right. There is no fixed shaft pointing backward. The entire propeller pod hangs vertically beneath the hull and can pivot in a complete circle.
It is exactly like the spinning caster wheels on the bottom of a grocery cart.
That's the perfect analogy.
You know how you can push a grocery cart sideways down an aisle or spin it in a tight circle without moving forward at all? An azimuth thruster gives a vessel that exact same total directional freedom.
And because of that incredible agility, azimuth thrusters are predominantly used for small-sized boats like tugs and ferries.
Right, because a ferry is constantly docking and undocking, navigating tight bays all day long, and a tugboat's entire job is to dance around bigger ships, pushing and pulling them from every conceivable angle. They need to move like water bugs.
They do. And this raises an important question about how different vessels require completely opposed propulsion strategies based on their daily tasks.
How do you mean?
Well, you have the massive cargo ship designed to cross oceans. It demands straightforward, simple, brutal efficiency. A single massive propeller and a huge rudder. It willingly sacrifices low-speed agility for high-speed reliability.
Right.
But on the other hand, you have a tiny tugboat meeting it at the harbor. It doesn't need to cross an ocean. It needs 360-degree azimuth agility to wrangle that giant cargo ship into place. They are two halves of the exact same global supply chain, utilizing completely different applications of fluid dynamics.
Man, we have covered a vast amount of engineering today, so what does this all mean for you? Well, the next time you happen to see a ship gracefully pulling into port or you are watching a ferry glide across a bay, you aren't just going to see a floating metal box anymore.
No, definitely not. You'll see the invisible mechanics working furiously beneath the surface.
You will visualize the immense pressure differential gripping the blade of that rudder. You'll picture the specialized pitch of those incredibly strong nickel aluminum bronze alloys slicing through the water, fighting corrosion and torque.
And the thrusters, too.
Yeah. When you see a ship slowly, impossibly sliding sideways toward the concrete dock, you'll know it's the transversal thrusters inside those hidden tunnels gently pushing it home. It completely changes how you look at the vessels powering our world.
It really does. And, it leaves us with something incredibly profound to consider about the future of this engineering.
Oh, listen.
We learned today that highly effective systems like the contra-rotating propeller are often completely abandoned on large vessels purely because of their structural complexity. Simple scale's better.
Right.
But as global shipping demands push cargo vessels to become exponentially larger and vastly heavier every single decade, will we eventually hit a physical limit?
Oh, I see what you're saying.
Right. Will we reach a point where traditional fixed-pitch propellers and massive steel rudders simply fail to scale up any further? Will the sheer complexity required to push the gargantuan leviathans of the future force us to completely reinvent how marine vessels move through water entirely? It is an engineering horizon that is rapidly approaching.
That is crazy to think about. And on that note, we'll leave you to think about the massive, invisible forces silently pushing the world's economy across the oceans. Thanks for joining us on this deep dive.